Okay, so it started recording. Right. So in the previous classes, we saw some basic information theoretic inequalities. We started by proving the Jensen's inequality, which says that for a convex function f, the expected value of f of x is greater than or equal to f of expected value of x. We also saw the log sum inequality, and then we used that to prove the following properties of the information measures. We saw that the KL divergence is a convex function of the inputs PQ. The entropy is a concave function of Px, and the mutual information is convex in Px for a fixed Py given x, and the mutual information is concave in Px for a fixed Py given x. So if you fix the input distribution, then the mutual information is a convex function of the channel parameters, and if you fix the channel, then the mutual information is concave in the input parameters. So this means that we can maximize the mutual information. So it's easy to maximize the mutual information and obtain the capacity for a given channel. And similarly, if we fix the input distribution, then we can minimize the mutual information with respect to Py given x. And while we've seen this problem, that is maximizing of the mutual information with respect to the input, when we talked about channel capacity, the other counterpart, that is minimizing the mutual information with respect to Py given x, is something that we didn't see in class. But for example, this is used in the problem of quantization, where the minimum rate of quantization can be obtained by minimizing the mutual information with respect to all Py given x, subject to certain constraints for a given Px. All right. So before we proceed to the next topic, it might be useful to just take a look at some numerical examples to get a better understanding of these convexity and concavity properties. So maybe let's start with the following binary symmetric channel. So we'll see the dependence of we'll see how the mutual information varies with respect to both the input and the channel. And the simplest channel that we can think of is the binary symmetric channel. Right? So the binary symmetric channel with crossover probability P. And let's say that the input to this channel is a Bernoulli Q random variable. So the entire system is specified by two parameters: the channel transition probability P and the input distribution, or the parameter of the input distribution Q. Right? And from what we've seen, the mutual information should be a convex function of P and a concave function of Q. Okay, so let me just share another window. Okay, so is this clearly visible? Okay, so here I'm considering a binary symmetric channel with a Bernoulli Q input, and I want to compute and I'm going to plot the mutual information as a function of P and Q. Okay, so here I've written some functions just to compute the mutual information, and first what I'm going to do is I'm going to fix a Q. I'm going to fix the input distribution and vary the crossover probability. Right. So let's say that Q is equal to 0.4. So the probability that the input random variable is 1 is 0.4. And I'm going to plot this as a function of P. Right? So here I compute, so to compute the mutual information, I need h of y and h of y given x. For this, I need to compute h of y, and this is what P of y equal to 0 turns out to be. Right? And I just compute h of y and h of y given x. So if I plot this with respect to P, I get this convex function. Right? And no matter how I choose Q, I still get that the mutual information is convex. And in fact, it is minimized when P is equal to a half. Right? So no matter what I choose Q, the minimizer of IXY is always P equal to half. Can someone tell me why this is the case? Yes, anyone?
Hello, sir.
Yes.
Sir, since it's 1 minus entropy, the
Okay.
capacity is 1 minus entropy. So at T is equal to half, entropy is maximum, and therefore the capacity is minimized.
So yeah, so what you're saying is talking about is the capacity, right? So the capacity is for a specific input distribution, right? Here I'm choosing like the input distribution could be arbitrary. So you're close, but the reasoning needs to be slightly different.
Output is independent.
Correct. So if P is equal to a half, then the output is independent of the input, and therefore the mutual information. So the mutual information gives you an achievable rate, and since the output is independent of the input, you can't achieve any positive rate over this channel. So the minimum possible mutual information is of course zero, and it is achieved when P is equal to a half. Right? And this is for yeah, so it's for any binary symmetric channel. Right. So now let me fix the input distribution P. Sorry, let me fix the channel transition probability P and vary Q. Right. So let me say that P is equal to 0.1. I'm going to compute the mutual information and plot it as a function of the input distribution Q. And once again, I get a nice concave function over here. And no matter how I choose P, the capacity, the mutual information is always maximized when Q is equal to a half. So if I take Q equal to 2.7, then or 0.9, then the maximum value of the mutual information changes, but the maximizer Q is the maximizing Q is always the same. It's also always equal to half. Can someone say why this is the case?
Hello. The information can be represented as a function of h of x minus h of y given x, and h of x is maximum when q equals half.
Your mic is in mute, sir. Sir, your mic is in mute.
Can you hear me?
Yes, sir. Now I can.
Okay, I'm not sure how that got muted. Right, so the mutual information is h of y minus h of y given x, right? So what can you say about h of y given x for a symmetric channel, for a binary symmetric channel? Does it depend on q? Yes, anyone?
Independent of Q, only depends on P.
Correct. So it only depends on p, right? Because h of y given x is basically the sum over all possible x of h of y given x equal to x times p of x. And for a symmetric channel, h of y given x equal to x is the same for all x. So whether x equal to 0 or 1, you still have the same h of y because it's a symmetric channel. So therefore, h of y given x is really independent of what the input distribution is. But again, it's only for a symmetric channel. And in this case, h of y given x is independent of q with the input parameter q. And therefore, the mutual information is maximized when the entropy of y is maximized. And what is the maximum possible value of h of y? Yes. Yeah, so it's equal to 1, right? And when do you get h of y equal to 1?
When y is uniform.
Correct. So when y is uniform. And when is y uniform? So for what value of the input is y uniform for a symmetric channel? So in particular for a BSc, for BSc P, no matter how you choose P, if you choose Q equal to half, then what is the output distribution? Yes. So for a binary symmetric channel, if the input is uniform, then what can you say about the distribution of the output y?
Uniform.
Uniform, right? And does this depend on P?
No, sir.
It doesn't, right? So irrespective of what the channel transition probabilities are, for a binary symmetric channel, the output is uniform if the input is uniform. And uniform output maximizes h of y. So the maximum of the mutual information is achieved when q equal to half. And this is irrespective of what p is equal to. Right? Okay, so that's for a symmetric channel. What if we have an asymmetric channel? And let's see the following. All right, so let's look at a binary asymmetric channel described by two parameters, P01 and P11. So unlike the binary symmetric channel, where the probability that 0 becomes a 1 is the same as the probability that 1 becomes a 0, the binary asymmetric channel treats zeros and ones differently. So given if the input to the channel is bit 0, then the output is 0 with probability 1 minus P01, and it becomes a 1 with probability P01, right? And if you transmit a 1 across the channel, then you receive 0 with probability P1 minus P11, and you receive 1 with probability P11. Okay, so P11 is the probability that the receiver gets 1 given that the input is 1, and P01 is the probability that the receiver gets 1 given that the input is 0. Okay, so if you choose P01 equal to P and P11 to be 1 minus P, then basically you get the binary symmetric channel. So this is a more general form than the binary symmetric channel. Right? So now let's see what happens for this particular channel when the input is again Bernoulli Q. Right? So the binary asymmetric channel. So for the binary asymmetric channel, I still compute the mutual information for different values of Q for a fixed value of P01 and P11. Okay, so if I plot the mutual information as a function of Q, I get something like this. So it's once again concave as we expect. So given the channel, the mutual information is a concave function of the input distribution. But now we see that the mutual information is not maximized when Q equal to half. So it's around 0.6. So for a binary asymmetric channel, the maximizing input distribution need not be uniform. Okay, and let's see if I change P01 to be 0.01 and P11 to be maybe 0.8, then I get something like this. So once again, the maximizing input distribution is not uniform, It's something close to uniform, it would be Bernoulli 0.45 or so. And but the mutual information is still a concave function of Q. All right. So now that we've seen the mutual information, let's see what happens for the KL divergence. Right? So let's look at two distributions, Px and Qx, where Px is Bernoulli P and Qx is Bernoulli Q. And I'll plot the KL divergence as a function of P for a given Q. Okay, so I fix P, I fix one of the distributions P, and then I'll plot this as a function of Q. All right, and this is what I get. Right? So this is a plot of the KL divergence for as a function of Q for a fixed P. So here, what is the minimizing Q? So what value of Q minimizes dpq?
Equal to P, 0.4.
Right, so correct. So the KL divergence is we've seen is always non-negative, and it's equal to 0 if and only if the the two distributions are the same. Right. So when Q is equal to P, then the KL divergence is minimized and it's equal to 0. Right. But it's still always a convex function. All right. So any questions so far?
Sir, can you explain the BSc part once again?
So which
The
part
BSc,
in the which part in the BSc?
where we fix Q and fix P, the two different cases.
Okay.
Just the plot. I didn't
Okay.
understand.
So for the BSc, right, the binary symmetric channel, right? Is that right? So is that what you want, the binary symmetric channel?
Yes, sir.
Okay, fine. So again, for the binary symmetric channel, now there are two parameters. One is the input distribution, which is Bernoulli Q, and the channel transition probability, which is specified by P. So if I fix the channel and vary the input distribution, then we're going to get then the mutual information is going to be a concave function of the input. Right? So the input distribution parameter Q. And at least for the binary symmetric channel, it's of course concave, and the maximizing input distribution is Bernoulli half. Right? And we've seen that is because for a symmetric channel, h of y given x is independent of x, independent of px, and therefore ixy is maximized when h of y is maximized, and h of y is maximized when ixy maximized when h of y is maximized, and h of y is maximized when h of x is maximized. So that's when the input is Bernoulli half. Right. So once again, this is always concave. Right. Now if I fix the input distribution and vary the channel, so I fix the input to be Bernoulli 0.9, and I vary P of Q. I vary P and plot the mutual information as a function of P. Then I get a convex function. right? And the mutual information is minimized. So in some sense, for this input distribution, the worst case channel is when P is equal to half, because that is when the mutual information is minimized. And when is the mutual information minimized? It is minimized when P is equal to half. And why is it minimized at P equal to half? It's minimized because when P equal to a half, the output is independent of the input, and therefore the mutual information is always equal to 0, right? Any question? Was that clear?
Yes, sir. In the assignment, there was a similar question like z is equal to x or y. So
Okay.
when we found the distribution of z, it was Bernoulli half.
Okay.
Also, the x was Bernoulli half,
Uh-huh.
and y was Bernoulli p.
Yes.
So when we see it is similar to a binary symmetric channel.
Exactly.
Yes. So in that case, mutual information between x and z was asked.
Yes. And what did you get?
So in assignment we did like x and z are independent and therefore mutual information was 0.
Correct. That's true. So it's basically the same thing. That so here z is, you can think of x as the input, z as the output of the channel, and y as the noise, right? So of course here the variables are different, but in the assignment you can think of x as the input, z as the output, and y to be the noise, and therefore if when say y is equal to Bernoulli half, then the mutual information between x and z would be equal to 0, right?
Sir,
Yes,
I'm
please.
having the doubt.
Uh-huh.
Sir, fix P and vary Q. Just go to that portion, sir.
Fix P
The
and
previous
vary
one.
Q. Yes. Okay.
Uh, P vary Q. Sir, yeah. So this mutual information h of I of xy is equals to h of x minus h of y by x. Sorry, this one. Sorry. So
So
this
yeah,
h of y by x, you said this will be independent of px, means
correct.
p.
For a binary symmetric channel. It's only
Yes,
for a
sir.
symmetric channel. Okay.
So sir, this isn't become zero like that we get in assignment x I of x
So
z is
so so
equals
so
to
these are
0.
two different things, right? So I'm not saying that y is independent of x. The random variable y is not statistically independent of x. So y is certainly dependent on x, but the entropy as a function of py given x and px, so h of y given x does not depend on p of x.
Okay, fine, sir. I
That's the only thing.
misunderstood.
So those are two different things. So I'm not talking about
Yeah.
independence of random variables. I'm just talking about the independent, that the expression does not depend on p of x. Right?
Okay, sir.
Any other questions?
So could you just scroll down to binary asymmetric channel, the graph?
1 second. Right. So here, can you see it now?
Like I didn't get the reasoning why mutual information should be maximized at the point.
At what point? So the mutual information is always a concave function of the input distribution, right?
Yes, sir.
Okay. So it's just saying that Q equal to half is not necessarily the maximizer. The maximizer is something between 0 and 1.
Like, is there any straightaway formula type which can exactly give you where's the point it is?
No, so you will need to sort of optimize. You can get a formula, but it's going to be a little more complicated than just something very simple function of P and Q.
Okay.
Sorry, function of P01 and P11.
P10 is. Okay.
Yeah. Any other questions? All right, so now that we've seen these properties of the mutual information and entropy, let's see some more. Let's move on to a slightly different topic, and that is the following. Let me just. Okay. So we've seen that the mutual information is maximized, can be maximized to give you the capacity of the channel. The maximum rate of transmission is the capacity, which is the maximum of the mutual information between X and Y when maximized over Px. So the channel is specified by Py given X. The input to the channel is X. The output of the channel is Y. So now this is true irrespective of how X and Y are distributed. As long as it's a memoryless channel, the capacity is always the max of Ixy maximized over Px. Right? So here is one possible question. Now, what if I sort of do some pre-processing or post-processing at the output? Can I increase the capacity of the channel? So in particular, let us say that I do some post-processing at the output. I'll introduce a new sort of sub-channel, P Z given Y. Okay, so this is artificially done at the receiver. Right? So effectively, the effective channel becomes Pz given Y. Right? And the capacity of this channel from X to Z would be C prime, which is the max overall possible Px of I of X Z. Correct? So is it possible that C prime is greater than C? So can C prime be greater than C? Can I choose a Pz given Y so as to increase the capacity by doing this sort of post-processing? Or if I do some kind of a pre-processing at the input. So let's say that I have Py given X, the input is X, the output is Y. Can I do some pre-processing at the input? Maybe Pu given X, right? So that the effective channel now becomes Py given U. And now the mutual information, the capacity would now be C double prime, which is the maximum overall possible Pu of I of Uy. Right? So is it at all possible that the capacity can be increased by doing this sort of pre-processing or post-processing? But it turns out that, in fact, that is not the case. So no matter what kind of pre-processing and post-processing you do, and note that this pre-processing or post-processing could be completely general. Even if the channel is binary, so maybe X and Y are both binary, you could have Z to have any alphabet you want. It could be ternary, it could be quaternary. You could have like 10 different inputs, outputs. And similarly, in pre-processing, the size of U could be whatever you want. That doesn't matter. But even then, it turns out that the capacity indeed cannot be increased. And this is given by the so-called data processing inequality. The data processing inequality, which says the following. So if I have three random variables, X, Y, and Z, such that they form a Markov chain. So X, Y, Z form a Markov chain. And note that here indeed X, Y, Z form a Markov chain. So if I do some post-processing, then given Y, Z is independent of X, right? And similarly here, if I do some pre-processing at the input, then conditioned on X, Y is independent of U, right? Because X is sufficient to determine Y, irrespective of what U is. So X, Y, Z form a Markov chain, which means that P Z given X and Y is the same as P Z given Y. And similarly, the reverse also holds. So P X given Y and Z is the same as P X given Y. So if we have these three random variables which form a Markov chain, then the mutual information between X and Z can be no larger than the mutual information between X and Y. And similarly, the mutual information between X and Z can be no larger than the mutual information between Y and Z. So basically, if you have a particular system X to Y, then no amount of post-processing can increase the amount of information that you get about X from Z. So note that the problem, so here the problem is you have some input X that you want to estimate or you want to get information about, but what you observe is Y. And what the data processing theorem says is that no matter how you do this post-processing to get Z from Y, Z can give you no more information about X than Y does. And similarly, if you do some sort of pre-processing at the input, and the goal is to, or let's say, you have Z and you want to find out, so if Z is the input and Y is the output, then the mutual information, then the amount of information that X gives about Z can be no larger than the information that Y gives about Z. All right. So let's see how one can prove the data processing inequality. This is simply a consequence of the chain rule of mutual information. So basically, all you do is take up a particular mutual information, and then using the chain rule, you expand it in two different ways, and that is it. So it's a nice little trick. So we'll start with. So what we want is the mutual. Let's try to prove the first statement. Ixz is less than or equal to Ixy. So in order to do this, we look at Ix, the mutual information between X and the pair YZ. Right? So can you tell me how you can expand this using the chain rule of mutual information?
So
Yes.
I of x of y
I of x, y.
plus
Yes.
I of x of y by z.
Are you sure?
X of z. First one is x
Right.
of z.
Okay, fine. So if you want to write that way, so I of xz plus I of xy given z. So this is one way to write to expand this term. Now this I claim is greater than or equal to I x z. Can you tell me why?
Conditioning. This
Not really.
sum of two
Correct.
terms are there.
Okay. So what can you say about I x y given z?
It's non-negative.
Correct. It's non-negative, and therefore it's greater than or so it's greater than or equal to 0. So I x y z is greater than or equal to I x z. Okay, so we have this. Let's write the mutual information and expand this mutual information between x and yz in a different way. So I can write this as ixy plus ixz given y, right? So now what can you say about the second quantity here? Can you say something about the second mutual information, the mutual information between x and z given y?
0.
And y?
Z given y is completely independent from x.
Correct. So maybe to get that a little better, let's expand ixz given y. So this is h of x given y minus h of x given yz, right? And we've seen that x, y, z forms a Markov chain. So conditioned on y, x is independent of z. So this is h of x given y minus h of x given y. So this is equal to 0. Right? So this quantity is 0. So I x, y, z is equal to the mutual information between x and y. But we've already seen that the left-hand side is greater than or equal to the mutual information between x and z. So the mutual information between x and y is greater than or equal to the mutual information between x and z. So no amount of post-processing can increase the information that you get about x from y. All right. Any questions? All right, so this is the data processing inequality, and this is very frequently used both in information theory, statistics, and machine learning. So basically, if you're trying to estimate a particular random variable x, and you want to say, and you're given y or you're given z, then the question is, how do you choose this z given y in order to maximize the amount of information that you get about x, right? So let us say that the goal is to estimate x from y, okay, and you want to somehow compute some function of y, right? Just maybe because you want to sort of reduce the amount of computation required. Maybe it's easier to estimate x from f of y than it is to estimate from y due to computational complexity reasons or maybe some other reasons. Right? So the question is, how do you choose this f of y so that you still retain all the information about x. And now you know that the mutual information between x and f of y can only be less than or equal to the mutual information between x and y. So we want to choose an f such that equality is still satisfied. And one way to choose this is, suppose that we can somehow choose f of y such that, of course, f of y obviously forms a Markov chain, because f of y is a function of y, and given y, f of y is independent of x. If we can choose f such that x, f of y, and y form a Markov chain, if you can choose such an f, then again from the data processing inequality, you have that the mutual information between x and y can only be less than or equal to the mutual information between x and f of y, which implies that the two mutual informations are essentially the same. So the mutual information between x and y is the same as the mutual information between x and f of y. So f of y basically contains all the information you need about x, correct? So basically there is no loss of information in going from y to f of y if you want to estimate x. So such an f which satisfies the following property, that of course x, y, f of y forms a Markov chain, and x, f of y, y forms a Markov chain. So if you have a function f which satisfies the property that x, f of y, and y form a Markov chain, then f is said to be a sufficient statistic for x from y, or given y. So we say that a function f, or f of y, is a sufficient statistic for x given y if the following Markov chain relationship holds, that is, y is independent of x given f of y. Right? Any questions?
Sir,
Yes, please.
I didn't exactly understand how f of y is working in the second case, because we need y to first to get, like, we need something to process on it, then we can get f of y. But how are we able to get first f of y and then we are extracting y from that?
So we're not getting f of y, right? We're just talking about the relationship between the join. So basically you have three random variables, right? You have x, you have y, and you have f of y. Of course, f of y is obtained from y, right? That is always true. But if the joint distribution of x, y, and f of y is such that the probability of f of y, the probability of, so p x given y and f of y is the same as the probability of x given f of y, then we say that f of y is a sufficient statistic for x given y. So one way to think about this is that f of y could be an estimate for x, and in some sense, and in one sense, the best estimate f of y would be one which forms a sufficient statistic for x. All right.
Okay, sir.
So here's a sort of, maybe this takes a very simple example. So let me see. So here's again a very, it's sort of a trivial example, but let us assume that you have x, you have a random variable x. Let us say this is Bernoulli P. Okay, and maybe y consists of x and x XOR e for some Bernoulli random variable e. Maybe it is Bernoulli q. And my f of y, so this is y is equal to y1, y2. Where y1 is x, or maybe let me put it in a slightly different way. Okay, so this is x plus e1 and x XOR e1 XOR e2, where e1 and e2 are Bernoulli q and are independent of each other. Okay, so this is y1, y2, where y1 is x1, where y1 is x XOR e1, and y2 is x XOR e1 XOR e2. So the input is, so x is just a single bit, but y is basically a pair of bits. Okay, and my f of y is just basically y1. Okay, now can you see that given f of y, x is independent of y? So p of y given f of y and x, this is the same as p of y given f of y. Do you agree?
Yes, sir.
Correct, right? So in other words, x, f of y, and y form a Markov chain. Correct. And basically what we're saying is that f of y contains all the information about that there is about x in y. Right? So we're sort of shrinking the space of y. We're throwing away all the information that is unnecessary. So f of y contains everything that we need to know about x, and we're also getting rid of extra baggage. All right. Any other questions? All right. So now we've seen that, of course, that pre-processing and post-processing don't really increase the capacity of a channel. But is there something more that we can say about the channel itself? So in particular, let us say that we have you have some kind of a channel where the input is x, the output is y, and from y you get an estimate of x. Let's call it x hat. Okay, so of course in any communication problem the goal is to estimate x from y, and since x hat is a function of y alone, x y x hat forms a Markov chain. So x y x hat forms a Markov chain, and therefore so what we're interested in is the so-called probability of error, which is the probability that x hat is not equal to x. Okay, and the goal is there any fundamental limit on the probability of error? Can we say that the probability of error is always lower bounded by something for a given channel py given x? So if all we are told is the distribution px and py given x, then can we say something about this probability of error? Okay, and in fact we can. That's given by Fano's inequality. So the Fano's inequality says the following, that h of y given x, or I should say h of x given y, is always in some sense a lower bound for the probability of error, but more so h of x given y, just using the data processing inequality, is less than or equal to h of x given x hat. This you can show using data processing inequality, but this is less than or equal to the binary entropy of the probability of error plus PE log cardinality of x. So if you look at the probability of error as a function which varies between 0 and a half, then it turns out that the right hand side is an increasing function of the probability of error. So if the uncertainty about x given y is larger, then so is the probability of error, PE. Right? So the Fano's inequality gives a lower bound on the probability of error for any arbitrary given random variables x, y, and its estimate, and the estimate of x hat. Right? Any questions? So I won't have time to prove Fano's inequality in class, but I've already uploaded some notes for all of these, so you can take a look. In the next class, we'll have a slightly long quiz, and basically, yeah. So the classes themselves end today. I'll maybe record another video to just discuss what the applications of all of these inequalities are. We've seen a bunch of properties of information measures, but we haven't really used them yet. Unfortunately, we don't have enough time to discuss that in the regular classes. But I've already uploaded some notes, so we'll see how these properties of information measures can be used to prove converses. So basically, so we've seen that there exist codes which achieve a certain rate. We've seen that there exist codes of rate equal to ixy which achieve a vanishingly small probability of error. Right? So whenever r is less than c, the capacity, we can drive the probability of error down to 0. But it turns out that if r is greater than c, if you try to transmit at a rate greater than the capacity of a channel, then the probability of error, in fact, cannot be driven down to 0. So there exist no codes which asymptotically achieve a rate greater than capacity and at the same time achieve a vanishingly small probability of error. If you try to transmit at a rate above capacity, then the probability of error will be strictly greater than 0. Right? Yes, those who have class can leave, but if you have any questions, I'd be happy to answer them now. Any questions?